Okay, let's solve an example problem using conservation of energy. Let's say we've lifted a child in a swing. Everyone's been on a swing before. Let's say we've lifted a child a meter off the ground and then let the child go. So we see a child here, and this may be a little bit hard for you to see, but we have a child here that's been lifted off the ground and allowed to swing back and forth. And we'll notice that at the very tops of the swing, we have only potential energy. The child actually momentarily is not moving, so it has no kinetic energy at the very ends of his or her swing. And at the bottom of the swing, right down here at the very bottom, the child would have no potential energy, almost on the ground, and would have all kinetic energy. So if the child's been lifted a meter off the ground, let's look at how to solve a problem like this. Recall this is mechanical energy, conservation, and so we have the sums of the potential and kinetic energy at the very beginning equals the sum of the potential and kinetic energies at the end. And you get to choose when the beginning and the end is. I'm going to choose the beginning to be just before the child's released, and the final position to be at the very bottom of the child's path. So at the very beginning, before we've released the child, it has no kinetic energy. So this is 0, right here. And at the very bottom of the swing, the child has no height, so it has no potential energy at the bottom. So we can rewrite this as the potential energy at the beginning equals the kinetic energy at the bottom. And remember, potential energy is mgh, and kinetic energy is 1/2 mv squared. So notice there's a mass in both of these terms. So if we divide both sides by mass, the masses will be divided out to 1. And just leaving the acceleration due to gravity times the height on the left equals 1/2 of the velocity squared on the right. So now let's solve this problem. So the acceleration due to gravity is 9.8 meters per second each second, and the height is 1 meter. So over on the left we're going to have, and I don't have the pointer the right color, let's take white. Over here on the left we're going to have the acceleration due to gravity, which is going to be 9.8 meters per second each second. And we're going to multiply that by the height, which is 1.0 meters. Not sure where these horizontal lines have come from, so we're going to get rid of them. And that's not working, so we're going to stay with ballpoint pen. That equals 1/2 of the final velocity squared. So how do we solve this? We've got 1/2 of the velocity squared on the right and 9.8 meters per second each second times 1 meter on the left. So what we're going to do is multiply both sides by 2. If we do that, we're going to multiply the right side by 2. 2 times 1/2 is 1. And so then we have to multiply the right side by 2 as well. Well, we already have 9.8 times 1, that's just 9.8, and 2 times 9.8 is going to give us 19.6. And that's going to be meters squared per second squared. And that equals v squared. So in order to solve this, we're going to have to use a concept called a square root. So we don't want to know the square of velocity, we want to know the velocity of the child. So we're going to have to take this 19.6 and we're going to have to square root it. And if you do that, you get about 4.4 meters per second. So we're going to square root both sides, and we're going to get that the velocity equals 4.4 meters per second, because we have to square root the unit as well. The square root of a meter squared is a meter, and the square root of a second squared is a second. So we just end up with the unit meters per second. And just check that. Is meters per second a unit of velocity? Does that measure how fast a child would be moving? And the answer is yes. So this is how you apply conservation of mechanical energy to solve a simple problem. I will see you in class tomorrow.